Okay, so in this video I'm going to talk about intermolecular forces now. Intermolecular forces, as the name suggests, inter means in between. So these are the type of forces that are present in between the molecules. Okay, so in between the molecules would mean that if you have two molecules of water, they might have a type of interaction in between them, and that type of interaction is called intermolecular forces. All right, intermolecular forces, as I mentioned in the previous video, are either polar or non-polar. Polar are those bonds which have a difference in their electronegativity, whereas non-polar are those in which the electronegativity is almost the same or exactly the same. For example, diatomic molecules. The polar ones are compounds of a polar substance will almost always have nitrogen, oxygen, or fluorine. Whereas the non-polar, all hydrocarbons are always non-polar, all right, regardless of whatever type of hydrocarbon that is, all right. And then if we talk about the intermolecular forces, if we talk about hydrogen bonding, if we define hydrogen bonding, so hydrogen bonding is not actually a bond, okay, it's just an interaction. It's an interaction, it's not a proper bond like the covalent bonding or ionic bonding or metallic bonding. It's just an interaction, so it's very weak. And if it is very weak, then in fact there was an MCQ which was asking about the length of hydrogen bond compared to covalent bond, ionic bond, and metallic bond. So the length of hydrogen bonds is going to be the longest, because the longer the bond, the weaker it is. All right, this was actually an unusual MCQ that came in the recent exam papers. Apart from that, if we talk about hydrogen bonding, so the definition of hydrogen bonding is that for hydrogen bonding, first of all, you need to have the most electronegative elements on the periodic table. That is, you must have nitrogen, oxygen, or fluorine. All right, these nitrogen, oxygen, and fluorine must be directly bonded to a hydrogen through a covalent bond. All right, so what are the three key elements that we have in our syllabus in which these three elements are directly bonded to hydrogen? So for nitrogen, we've got ammonia. For oxygen, we've got water. And for fluorine, we've got hydrofluoric acid or hydrogen fluoride. Now in all three of them, we've got hydrogen directly bonded to NOF, one of the nitrogen, oxygen, or fluorine elements. All right, now there's an important point to note over here, is that these electronegative elements have a hydrogen directly attached to them. The hydrogen is going to be considered partial positive or electron deficient. Now the type of, if this is an electron deficient hydrogen, it can be attracted to the lone pair of nitrogen, oxygen, or fluorine, all right, of a different element. That's a key term to note. So if you've got two water molecules, two different water molecules, they will have a hydrogen bond between one another, all right, at which the hydrogen bond is going to start off from the lone pair of oxygen, and it's going to end on the hydrogen of the other water molecule. So in between two water molecules, on average, how many hydrogen bonds can we have at max? Think about this. We can have how many? 4 hydrogen bonds in between two water molecules. But if we talk about two ammonia molecules, we can only have 2 hydrogen bonds between two ammonia molecules. We cannot have 4 of them, all right, because hydrogen bond is always made between the lone pair of nitrogen, oxygen, fluorine and the hydrogen of another molecule which has that hydrogen directly bonded to nitrogen, oxygen, or fluorine. That, having said, completes hydrogen bonding. All right, so hydrogen bonding by definition is the type of attraction that exists between, it's the strongest intermolecular force that exists between an electron deficient hydrogen and a more electronegative element. More electronegative element includes nitrogen, oxygen, or fluorine. All right, so this wraps up hydrogen bonding. In the next video, I'll try covering the permanent dipole, and London dispersion.